Okay then. Good morning. Let's get started. Today we'll be looking at word embeddings. Finally, the word to it. What is the idea behind it and why it's popular, and what was the mm, key contribution of such embeddings. So before we start, I'd like to recap what we've seen so far in the course. First is we saw that with statistical machine learning, we need a way of representing the words as vectors. And we saw a very naive method of using one-hot encoding, where we take the entire vocabulary and each word is represented with 1 or 0. And we saw many problems. First is in that huge vector, only one position is going to have a value, so it's very sparse. We saw that in high dimensions, it's difficult to measure distance, it's difficult to search in a high dimensional space. So we have the curse of dimensionality. And then we saw that all these vectors were equidistant because only one position is going to be 1, so it's going to be like 0, 1, 0, 1, 0, 0. So all the vectors are going to have the same magnitude and they're going to be equidistant. So it does not capture meaningful semantic information. Now, as an improvement, there were the LSA vectors that dominated in the 90s, which were compact, so we didn't have these huge sparse vectors, and it had some sense of relatedness, but it did not capture synonymy or homonymy. Synonymy meaning each word having um, multiple words having the same meaning, and homonymy meaning each word having multiple meanings. So, how did we proceed from LSA to word embeddings? First is that we have this idea that we are not capturing as much semantics as we want. Next is we want a compact vector, which is the same thing we saw in LSA. And the idea was to incorporate context. Now, we saw even in disambiguation, if I have the word bank, I can look at the nearby words to disambiguate the meaning. A similar approach was used for word embedding. So how does context help? For synonymy, if I have a word and if I have multiple words that have the same meanings, that implies that they would occur in similar contexts. So the vector representation of various words that have the same meaning will be very close to each other. In homonymy, same word has different meanings, so the vector representation is sort of composed of all these meanings. So it's sort of similar to all the different meanings that are available for that word. So in any lecture with word embeddings, you'll see this quote, which is that a word is known by the company it keeps, written by a linguist in 1957. So the idea of incorporating these two is what led to word embeddings. It's also known as distributional semantics. So we are going to distribute the semantics over the vectorial space. That's what it means. And here we are modeling language as such, right? We are modeling words. So it doesn't matter if it is for, say, classification or sentiment analysis or any particular task. The next question is, how do I model this? Do we want a vector for a word? Do we want a vector for a sentence? Do we want a vector for a document? That's the next aspect we have to see. Now, distributional semantics belongs to the world of connectionist approach, but you can also build a vector using symbolic approaches, such as WordNet, which will incorporate some semantics. We'll of course be seeing the neural net version of word embeddings in this lecture. So we will be looking at word2vec in this lecture, but there are other word embeddings such as glove, contextualized embeddings, and so on. We'll be seeing some of them, but the others you can look up and see how they differ from the basic word2vec that has been proposed here. So the original idea just had two layers, and still it was very useful and efficient. And how we train these vectors is to learn a representation as a byproduct of another learning task. So you might fail at this task actually, but because of the way you've designed this problem, you will learn a better representation. This will become clear in the next few slides. So the idea is I have a certain input and a certain output and a hidden layer. That's it. There's just two layers, and we learn the representation in this hidden layer. So what do I mean by that? Here we have two models, which is the skip word model and the continuous bag of words. Coming back to our central theme, we are going to learn the representation of a word given its context. So I can model this as two tasks. In skip word, what I do, I have a given word and I predict what the context is. In SIBO, what I do, given the context, I predict what the word is. So if I say the cat is running now, the word cat is surrounded by the context, the, running, and now. Now in SIBO, I give the, running, now and get the word cat. These are the two inverse architectures we will be looking at. How are we going to model this? Before that, let's go over quickly some notation. V is going to be the size of the vocabulary, C is the size of the context, W is the weight matrix, and X is an indicator vector. Indicator vector basically means our one-hot encoding, which will say which word in the vocabulary. So now, I will be showing an example of CBOW before going into the map. So if we have a sentence, the cat sat on the floor, and our window size is 2, then our central word is sat, -2 is the cat, and +2 is on floor. So in CBOW, so you can see WT -2, T -1. Okay, here W is word, not weight, sort of overloaded. But yeah, WT +1, WT +2, and W of T. You can sum them, you can in a very naive way. But what we will be doing actually in the neural net is, of course, we'll be sending it to a hidden layer and then getting the output. So how do we model this in a neural network? Our input and our outputs for training are one-hot vectors. So you might think, how are we learning the representation? Well, we'll be sending the one-hot vectors to a hidden layer, and this will be compact, not as big as the vocabulary, and then we'll have the output layer. Now, while I am learning this task, that is given the context and predicting the word, I will end up learning a hidden representation or a compact representation for that particular word. So that is our aim in word2vec, and it works, though it is very simple, because of the staggering size of text data that is available today. That is the key reason such a simple network works, and we'll also be seeing that the way of learning it is exactly the same. It's the same back propagation and everything. So it becomes very intuitive, and it scales very well. So to come to the notation, we have a weight matrix, which is of the dimension vocabulary cross D, where D is the compact size of the compact representation we want to learn. So given an input layer of vocabulary dimension, these are the same sparse vectors we saw earlier, and here it is the inverse. I mean, it's not the inverse of this, but the dimensions are the inverse. It's D cross V. because we go from the hidden dimension to the vector side. Now, how do we get, we have this W V cross D matrix. How do we get the vectorial representation for a word? So if I arrange all the words in alphabetical order, I have this big W cross V matrix. But what I am interested in is the vectorial representation of one word. Say this one. All I'll do is mathematically do X transpose W, you will get the vectorial representation of that. It's basically a vectorial way of representing what we might implement as, say, a hash table or something like that. So now, coming back to our example, which had cat, on, and sat here. First, what we do? We take the word matrix and the weight matrix, and we apply it for xcat, similar to what we saw here, and get the vectorial representation. And here we get the vectorial representation. Oh yes, in context we do sum it up and send it to the hidden layer. And then at the output layer, in the training example, I know that this has to be a 1. Similar to a backpropagation algorithm, I will be sending the errors back and changing the weights. So this W cross V matrix, that W cross D matrix that I have here is our word embedding matrix. So first I'll do it for on and get the hidden other one vector, and then I'll do it for cat. So we'll be seeing what softmax is in this lecture, and basically it is an activation function very similar to the sigmoid function we saw earlier. And then when we apply that, we get something very similar, say, to 1. Then, of course, we will be doing backpropagation and putting the weights back, as I said before. So now, when you actually implement this, you'll see that it predicts very badly. You might not get the word at all. But this matrix is our key goal, and we get the word-to-vec representation. Now, the interesting thing is, if you see, the representation is in both this weight matrix and in this weight matrix. So which one do we take? That is an interesting question. So I think the original word-to-vec paper took the average, but in general, you can take either, both, and you can experiment which is better for your task and so on. Now we come to skipgram. Skipgram is a harder task. Given one word, you have to predict multiple words, but it's also equivalent to predicting multiple contexts. So it's harder, but it's also like a sort of stronger representation because it incorporates all of that into this. So once again, you have the one hot encoding, and you have to predict the one hot encoding of the others. And there's a concept called tying the weights here, in the sense the weights of both these parts of the network are exactly the same. So when I train them and change the weights, I will be changing weights for both at the same time. So before proceeding, I'd like to spend some time on the sigmoid versus softmax function. We saw the sigmoid function a couple of classes back, which is 1 by 1 plus e power minus x. The softmax function is slightly different. When I have a lot of variables x, it's e power x by sum of e power x. What does this imply? If you take a bunch of examples and plot the graph, you'll actually be surprised to find they look very similar. Then what is the idea, or what is the difference between the two we need to see? Both of them output values between 0 and 1. Both of them can be used to model probabilities because the not only do they output value 0 and 1, they will also sum up to 1 because of the way it is designed. So what's the difference? So sigmoid is actually a binary case of softmax. If you see the definition, this is 1 by 1 plus e power minus x, and this is e power x by sum of them. So in the binary case, when I is 0 and 1, you'll get back this particular function. So now that we have an idea what's the difference between sigmoid and softmax, let's explore why softmax is called softmax. So a hard max of 2, 3, and 5 would return 0, 0, 1. So it's basically the maximum of this vector. So 2, 3, 5 maximum is 0, 0, 1. Now the softmax on the other hand still assigns some values for the lower ones. If you compute using the formula I am given, what is the softmax of 2, 3, 5, you'll get 0.04, 0.11, 0.84. So still this is the maximum, but it is giving some value to the other two. So these can be interpreted as probabilities. Now, the interesting thing for us, especially in neural networks, is it's also differentiable, so you can measure the error while you do backpropagation and do gradient descent. And the second thing is our training data is never going to be perfect. For example, and especially in text, when you take a word and you are predicting the context, you cannot 100% be sure that given this word, this has to be the context. Because I'm sure you can come up with any number of sentences with one particular word. And it's that way, it models the real world well, where you're not saying that this is the answer, but it is probably the answer. So now we come into the math, what is happening, how we do backpropagation for word to word. So here we are learning to predict the surrounding words. So it's the skip-gram model. So our objective function that we need to optimize is the probability of the context word given the word. So this is the vector representation of the word, and we need to predict the vector representation of the surrounding words. Minus m to m suggests the context that we are summing over, and t is the size of the data set. Now, previously in TF IDS, we saw log was used to bring the scale together. So if I have log 1000, it will come down to a number like 3 or 4. That was the advantage of using log there. Here we are using log because in probability, when I have multiple events, I'll actually be multiplying them. So across, actually what I should have done is across the training samples, I would have multiplied all these probabilities. But once I take log, the product becomes the sum. So it becomes much easier to compute, especially we need to keep in mind, this is after all a deep learning network. So your data set is going to be very large. And usually we also take the cortex to be around 5 to 10. So taking the log simplifies this quite a bit. So now we will be using the softmax function where W0 is the WO is like the outside word and W1 is the center or the input word. So we use a score to measure the similarity between them and then use the softmax. So here the score they've taken is the dot product or just the cosine similarity if they are normalized. And then since we take the score as that, it reduces to the dot product. So every word has two vectors, which is what is the representation if it is a center word and what is the representation if it is a context word. It This differentiation helps us in training the network, but as we saw before, we can use either of the representations, whether it is a center word or a context word, because what happens is that anyway, this weight will involve some of the context information, and the context weights will involve some of the so-called center word representation. And of course, we can take the best of both worlds and take the average. So, um, just reiterating what the function is. But here, what I need to do is replace this with this. And that again, it becomes very useful for us because we have taken the softmax function, and the softmax function, when you take log, a lot of things get cancelled and it becomes um, simple to compute. To some extent, we'll be seeing some problems. So the major problem is there's anyway a summation in the gradient. Now we saw even earlier when we have a summation, then it becomes the complexity becomes O of n cubed because you'll have three for loops, one for the training data, one for the weights, and one for the input variables. So to solve that in the previous case, we moved on to stochastic gradient descent instead of the original gradient descent. Still, even after having stochastic gradient descent, in this particular case, because of the way the data is, first of all, our vocabulary is huge. That is why one hot vectors were, after all, not useful. So we use two different ways of crossing this problem. One is negative sampling and the next is subsampling. These are there in the original word-to-word paper or the paper that followed that, I'm not very sure, but by the same authors, which describe how we can optimize over these values. So the idea of subsampling is to weed out words that are not important to your training. For example, if I have the word the in the context, it does not impart meaning to the center word because the word the occurs with everything. We want words that are differential and meaningful to that particular word. And as I said before, we'll be looking at the same idea in attention later on in the course, where we want to pay attention to words or to parts of the network that have importance. Now, we addressed this actually before with TF ideas, where the inverse document frequency accounted for such words because we saw words that occurred in multiple documents, and if a word is very frequent in all documents, then you know it does not lend meaning to the context or the word. In a very similar fashion, we build our context vectors such that these words are not counted as a function of frequency. So it's the same concept where instead of putting a score as IDF, I myself use this frequency and weed out the words from the training and how I design the context. So because I changed the training data itself, I call this subsample. The next interesting idea is negative sampling. So in negative sampling, what we do, as I said before, this calculating the sum over vocabulary is quite time consuming for weight updation. So what we do is we take the true, because we have a training data, we take pairs between the center word and the context and center word and random. I'll explain what I mean by that. So coming back to our example, we had this huge weight matrix. So your vocabulary would be around say a million or something like that. And your D would be around 100, 200, 300 or something like that. So in You can imagine your V cross D will be a million cross 300. Similarly, for the context. Now, what I do is I know that, say, this word is sat and this is cat. I want the weight vectors for sat and cat alone to change. So I will take the vectorial representation for sat, that particular row, change that weight alone. Similarly, for cat also I'll do that. But what happens is, in any training or any machine learning algorithm, your algorithm should not only predict what is correct, but it should also successfully predict what is wrong. Only then is it useful. For example, if I have an algorithm that for a two class classification, if it always predicts one class, it will seem 100% correct when it is predicting the first class. But for the other class, it might be, say, it will be zero, right? But um, depending, you might predict a test a thing of, say, it's 80% correct because 80% of your data had class 1. So computer scientists are interested not only in predicting how correct the values are, but also the wrong or the other class values. So what we do is we update the weight for the word that we know is there in the output. Also, the negative sampling word comes from the fact that we will also update the word for few random wrong um, values which are not there in the context. What is the difference in this? Before, when we updated the weights, we treated it as backpropagation and just percolated the errors backwards. So when we did that, when I see all the weight vectors, I'll actually not know which word I am changing, because the concept of word is a semantic meaning we are imposing upon this weight matrix. As far as the algorithm is concerned, it was just another backpropagation technique. So we are incorporating our interpretation in negative sampling and saying you don't have to update all the weights in this big matrix, but just what is relevant. And this scales very well, and we get pretty good representation for the hidden layer. So coming back, we'll see what is the difference between LSA and word to vec. Now, LSA trains very fast because it takes all the words and the documents, and then we do this matrix reduction of singular value decomposition, and it's a mathematical operation which converges quite fast. Word to vec, on the other hand, it is a function of the corpus size. We get better representations with bigger corpus, but it takes more time to train as the corpus becomes bigger. Now, LSA also reduces to a very small space, and it's quite precise. The skipgram and CBOV model, on the other hand, they involve a lot of recalculations, and it's that way it is inefficient. But as we saw before, it is not the task that is important, it is the hidden representation which is quite good. Now, LSA is used to capture word similarity, and that is what it is good for. Um, but the similarity is not a semantic, it does not capture much of semantic similarity. It's more of a frequency similarity sort of thing, because the idea of context is not there. And as I said, this was a frequency based similarity, so there is a disproportionate importance given to large counts, words like the and things like that. Uh, to overcome this, there was an improvement on LSA where instead of using the frequency in the starting Word document metrics, we use the TF-IDF score, and that led to a bit better representation. but still it is dominated by um, counts, because that's what LSA does. It counts and it brings about an elegant representation. The word to vec, on the other hand, it can capture complex patterns beyond word similarity, which we will be seeing in the forthcoming slides. Before that, let's quickly look at how word vectors are evaluated. We have two kinds of evaluation: intrinsic and extrinsic. Intrinsic means that it is evaluated on a subtask, meaning it is evaluated on how good the vector itself is. Extrinsic is it is evaluated on an NLP task, sentiment analysis, and so on. So, in some sense, especially when you come to the engineering aspect, you would be more interested in extrinsic evaluation. And intrinsic evaluation is more, it appeals more to researchers because you want to know whether you've actually modeled the language or not. So, for example, analogies. Man is to woman as king is to what? So, you want to see if the analogy is being maintained, and you can um, measure this over a data set as you have defined. So it evaluates word vectors by how well their cosine distance captures semantic and syntactic analogy. And the, this statement, what if the information is there but not linear, meaning that um, this has been designed as a linear model where you say that, okay, if I subtract this and add this, what is the value? But it might not be subtraction. It might be something like subtraction between the squares or the cube or something like that. So there is a relation, but it is not a linear relation. So there is a problem in this intrinsic evaluation, but we see that the approximately it is linear in the word to vec case. And so yes, the distance between man and woman is more or less the same as the distance between king and queen. So because we modeled it this way, here it works, but we need to remember that in the forthcoming word vectors, the relation need not be linear, and then this test would fail. Next is visualization. In the tutorial in the next hour, we'll be seeing how to visualize these word vectors, because you must remember that the word vectors are still, even though it is a reduced space, it's still in a space of say 300, 400 dimensions, and it's impossible to visualize such big dimensions. A naive way, of course, is to use things like principal component analysis, which I touched upon in the LSA discussion, where we take the dominant eigenvector and project onto that. And that would give us a one-dimensional or a two-dimensional vector if we take two eigenvalues. So PCA is a very common method of dimensionality reduction, and I'll not be taking the math behind TSNE, but that is how high dimensional things are visualized today. Not it, Going by the analogy, these are some of the analogies that were obtained from Vertivec, which is that Paris is to France, as Rome is to Italy, bigger is to big, as colder is to cold, sushi is to Japan, as bratwurst is to Germany, CU is to copper, as AU is to gold, and Windows to Microsoft, Android Google, and Montreal and Toronto, the sports teams, and so on. It is amazing to see what context can do. We already had frequency based measures in LSA, but context brings in a lot of semantic information and value to our word vector representation. The next key idea is that as the corpus size increases, our analogy tasks become better. And when I say big corpus, I mean big corpus. The first one you can see it has 1 billion tokens, 1.6 billion, 4.3 billion, 6 billion, and 42 billion. So that means your vocabulary vector V is going to be of size 42 billion. So you can imagine how much space it would take, how much time it would take to train this network to a reasonable level. Extensive evaluation, as we said before, it deals with using your word vectors for a particular NLP task. For example, text classification or sentiment analysis, and so on. There's another type of vector called fast text. What it does is instead of using a word level model, it uses a character level and combinations of characters and so on. So the vocabulary is a bit limited and it trains fast, which is why it's fast text, and it's able to adapt to new words that are not there in vocabulary. Word2Vec also adapts to new words in the sense, no, Word2Vec you cannot adapt to new words. You have to have the particular word to get a representation. Next, we'll quickly see the intuition behind Doc2Vec, which is basically a sentence to a vector. A sentence similarity involves not only just the sum of the words, but there's also a sort of structure to a sentence that we want to capture. And what we elegantly do is that when we train the network, we also add something called a paragraph ID in the beginning. So what this does is and we have the same task, which here we predict the next word that has to come. So the cat sat and then on. Instead of the center context which we had in Word2Vec, in Doc2Vec we are trying to predict the next word. Because of this, we have a concatenation here, and then this simple addition of an extra vector gets us a very unique representation for the document. Of course, naive way of doing document representation is taking the average of all the word vectors. You'd be surprised to see in real world examples, average of Word2Vec does better than Doc2Vec for certain tasks. We need to see how it evolves. So, for example, if I have a um, very different domain, in the sense it's not general and the domain is say very specific to physics or something like that, the words that occur in the sentences are quite different from what Doc2Vec might have been trained on. So average Word2Vec often gives us good document representations. But if your data set is quite large, say with 1,000,000 words or something, you can train your own Doc2Vec. So that all this discussion brings us to the key important contribution, which is pre-trained vectors. Now, as a user, as an engineer, I will not have time to build a vector over 42 billion words, right? So after training this network, we now have freely available vectors for words in Jensen, Spacey, and many other libraries where we just import them and use them. So if I have a sentiment classification task, I just take the vectors for each of the words, I take the average, and that is my vector input for a simple machine learning algorithm, maybe a decision tree or so. I have a compact vectorial representation to perform such a classification. And this is the fundamental idea that has empowered research in natural language processing. And we'll be seeing deep learning networks such as RNNs, LSTMs, and so on, sequence, transformer, the entire set of networks. All of them depend on these pre-trained vectors, or you might even learn them using that particular network, say RNN or something. But all of them use word embeddings. So without word embeddings, all this further analysis that has come would not be possible. So let's come to the advantages. It captures the simple addition of context captures both part of speech and semantic information, and it scales. You, though I said it takes time, it does not take as much uh, time as you would expect a 42 billion word corporate take, and it can be used by others. That is the next important one. And I mentioned Jensen here, but also like Spacey and things like that, which take word away. Disadvantages is, though the word vector has incorporated various senses, in the sense, while training, I have looked at various contexts and built the word vector model. But no matter that, when I see a word, there's going to be only one particular vector. So if I now input a sentence for the bank building is close to me, the vectorial representation of bank is going to be exactly the same whether this is the sentence or the sentence is the Bank of Ganga. So this idea led to development of contextual embeddings where you enter the sentence and you get different embeddings for the same word depending on the context. Next is that, yes, we saw syntactic, part of speech, all these aspects were captured, but complex aspects like what is the subject, who is the entity, and so on, not being captured. We saw that in dependency parsing where grammatical relationships could be captured, and that led to interest in graph embedding. So if I input a dependency graph, how do I convert it to words? How do I convert it to a vector? And how do I augment my deep learning network? So we'll be touching upon these as well in the course, but not as detailed as we have seen word to vec. So yes, thank you. That was the first lecture for the day. And any questions, and then we can take a break.
Ma'am, I actually have a general question.
Yeah, go ahead.
So we were talking about synonyms and homonyms. I just want to
Yes.
know how it would work with things like antonyms. So if you take good and bad,
Yeah.
contextually, won't they be the same when you get the vector? Because it's going to be nouns after, and you're going to have other adjectives that go with them, but the meanings
Mm-hmm.
of them differ very greatly
Correct.
if they're antonyms.
But in some sentences, yes, the context is going to be exactly the same, but there'll be other sentences to differentiate the context. So that is why they take the context width to be around 5 to 10 words. It's not going to be 2 or 3 words or things like that. So the negative sentiment behind bad and the positive sentiment behind good will come within these contexts. So that is how it happens. And regarding relationship with antonyms, what will happen is the distance between good and bad will be similar to another pair of opposites. So that is the sort of thing it means. And you are right, if the context is very small, it would not capture that. But that's why we have large context while training.
Okay, ma'am. So 5 to 10, that's the reason for having 5
Yes,
or 10 words as the context. Okay.
exactly. Thank you. That was a good question. In fact, there is research. Um, for example, in sentiment analysis, the difference between good and bad must be much larger than what the language would offer us. So there are separate representation learning techniques which we'll be seeing at the end of the course, which exaggerates this difference more based on the task. So that's also an interesting thing to look at.